one might ask, what if the spring mass system are along the vertical as shown here? Okay, here we have diagrams of the same spring mass system. Here's our spring. It is suspended from a stand. In this particular image, the spring is not stretched. It is at a relaxed position, and we just add the mass here. Because of that mass, the spring is going to stretch by an amount d to reach this new equilibrium position. So the new equilibrium position is such that the spring is stretched by an amount d. And then what we do is either pull it away from that equilibrium position or push it away from that equilibrium position and let go of it to get it to vibrate. Let me show an example of that. So here are the springs, 3 of them. We don't need the 3 of them, just one. And they're in equilibrium with no mass in there. So the first image is basically this, me holding on to the mass. And then I'm going to let go of it to the equilibrium position. Okay, let me put lots of friction so we get it to reach the equilibrium position quick. And I'm going to remove friction. Okay, so this is the new equilibrium position. This is D from here to here. So what I'm going to do is either compress it a little bit like I did here by an amount y, that's what's represented in the diagram, and let go of it. Now look what happens. It's going to vibrate. Okay, to stop it, I'm going to give it friction. Okay, or I can stretch it as well from that equilibrium position, and it's going to oscillate, it's going to vibrate as well. Okay, that's what we are talking about. The question is asking, what are the forces acting on the mass while it is vibrating? Of course, the forces acting on it are going to be the gravitational force that's pointing straight down and the spring force. Okay, that's what we are going to write right now. So when in equilibrium, at this position here, the forces acting on our mass are the gravitational force and the spring force. The magnitude of the spring force is K times D, and it's pointing in the upward direction. We have equilibrium, so KD in this case is equal to mg. Okay, that's what we get here. Sum of all forces is equal to 0. We have equilibrium. So KD is equal to mg, and we can solve for D. D is equal to mg over K. So actually, this is a way to find the spring constant. We measure D and solve for K. So this is my y equals 0 position. Y is this axis that I draw here. I chose it as the equilibrium position, the new equilibrium position. Now, in this particular setting, my free body diagram is going to look the same. Spring force upward and Fg downward. Of course, the spring force might be negative at some times and positive at some times. When it is pointing up, it's positive since my y is pointing up in the positive direction. Okay, now let's write it down. Let's write Newton's second law of motion down for this particular case. In the case shown here, the amount of stretching of the spring is going to be this much. That's the amount the spring is stretched relative to its equilibrium position here. So the amount of stretching of the spring is actually D minus Y. So in this particular case, my spring force is K times D minus Y. and the gravitational force is still mg. Now, if we write this down, that's kd minus ky minus mg. Remembering that kd is equal to mg from what we just found here, so that's these two cancel each other out, and we are left with the sum of all forces is equal to minus ky. And this should be equal to ma. In this case, I'm going to write it on top here. We have ma is equal to minus ky, or a is equal to minus k over m times y. This is exactly the same expression that we have for a horizontal spring, except we had an x here instead of a y. So in other words, whether the spring mass is horizontal or vertical, we still have simple harmonic motion.